It has to run on classical hardware, sitting right next to the quantum chip, reacting to problems faster than the human eye could ever perceive. For years, every quantum hardware company solved this exact plumbing problem their own way, building custom, proprietary, mutually incompatible connections between their own specific chips and whatever classical computing power they happened to have on hand. There was no shared standard, no common language. This is not chaos. This is simply what happens in the earliest years of any genuinely new technology. Dozens of brilliant engineering teams solving the same fundamental problem in dozens of different, incompatible ways, each one convinced their particular solution deserved to become the industry default. NVQLink was NVIDIA's attempt to end that fragmentation entirely, and the technical claim underneath it was genuinely audacious. According to NVIDIA's own launch materials, the interconnect promised to exchange data between quantum controllers and classical GPUs at a latency under 4 microseconds, a speed roughly equivalent to completing 100,000 round trips in the time it takes you to blink once. 9 of America's most respected national laboratories, Brookhaven, Fermilab, Lawrence Berkeley, Los Alamos, MIT Lincoln Laboratory, Oak Ridge, Pacific Northwest, and Sandia, all contributed to guiding the interconnect's actual technical design before it ever launched publicly. A level of institutional scientific involvement that separates a serious infrastructure project from a flashy corporate demo built purely for a keynote slide. And the breadth of quantum hardware companies willing to sign on that same day was, frankly, remarkable. 17 separate quantum processor builders, spanning superconducting circuits, trapped ions, neutral atoms, and photonic systems, essentially every major hardware approach currently being pursued anywhere in the field, all agreeing on day one to plug into the exact same interconnect, rather than continuing to build their own separate, incompatible solutions. Alongside them stood 5 companies specializing in the delicate control systems that actually operate quantum hardware in real time. United States Secretary of Energy Chris Wright even weighed in, describing NVQLink as providing the critical technology to unite world-class GPU supercomputers with emerging quantum processors, creating the powerful systems we need to solve the grand scientific challenges of our time. When a sitting cabinet secretary starts describing a corporate interconnect using language usually reserved for space programs, that tells you something about how seriously the people in that room actually took this launch. Here's where the story could have simply ended, the way so many ambitious infrastructure announcements in this industry eventually do. Another exciting keynote moment, another round of enthusiastic coverage, and then quiet, forgettable abandonment once the initial press cycle faded. That's the fate that eventually claims most technology launches this dramatic. NVQLink's actual first 10 months tell a genuinely different story, and the evidence arrived in careful, verifiable stages, each one considerably harder to fake than the last. The first real test of whether NVQLink would become genuine, usable infrastructure rather than a permanent slide in future keynote presentations came in March of 2026 at NVIDIA's GTC conference, roughly 5 months after the original announcement. NVIDIA released something called the CUDA-Q real-time API, part of its broader CUDA-Q platform, finally giving developers the actual software tools needed to write real code, exchanging data between a quantum controller and a bank of GPUs at genuinely microsecond level speed. Alongside this software release, Dell independently validated 4 of its own server models as certified real-time host platforms, successfully reproducing those same sub-4 microsecond latencies on commercially available, off-the-shelf equipment any well-funded research lab could actually purchase. Read that again, because it matters enormously. This isn't NVIDIA simply claiming its own technology works inside its own internal testing environment. This is an entirely separate, independently respected hardware company running its own tests on its own equipment and confirming the exact same core performance numbers NVIDIA had originally promised. In both science and engineering, independent replication is the single strongest form of evidence you can possibly ask for, and NVQLink cleared that bar within 5 months of existing. Independent replication of a latency benchmark only tells you the plumbing genuinely works, though. It doesn't tell you whether anyone actually wanted to use that plumbing for something real, and this is exactly where the following months got genuinely interesting. Throughout the summer of 2026, a steady, verifiable stream of specific named companies began announcing real technical integrations, not simply repeating NVIDIA's name inside their own press releases, but building the interconnect directly into their own control software and their own commercial product roadmaps. Atom Computing integrated NVQLink directly into its proprietary control system stack. IQM, a Finnish quantum computing company, partnered with Zurich Instruments to build a real-time quantum error correction demonstrator, combining a 20-qubit IQM processor, Zurich Instruments' own specialized control system, and NVQLink itself. A company called Elevate Quantum launched a commercially deployable open architecture quantum system called QPAC, with NVQLink-based GPU cluster integration explicitly written into its stated roadmap. Dirac, building quantum processors from silicon-based qubits, an entirely different physical approach from IQM's superconducting circuits, began using NVQLink specifically for calibration, auto-tuning, and benchmarking, the unglamorous but genuinely essential daily work of keeping a quantum computer running reliably at all. And in June of 2026, Quandela, a French company specializing in photonic quantum computing, technology using individual particles of light rather than superconducting circuits or trapped atoms, published a detailed technical case study explaining precisely why NVQLink mattered for their own specific corner of the industry, identifying a structural problem with how quantum cloud computing had traditionally treated QPUs as distant, high-latency remote resources, and showing exactly how NVQLink's direct connection solved it. Think carefully about why this specific pattern of adoption matters so much more than the original 17-company launch list, because it's the actual answer to whether this connection genuinely mattered or simply generated a nice headline. A launch day partnership list costs almost nothing. Companies sign on to exciting new industry standards constantly, hedging their bets, wanting to be associated with whatever momentum happens to be building, often without any genuine intention of building real, load-bearing infrastructure on top of that standard. What happened over NVQLink's first 10 months was categorically different. These companies were publishing detailed technical case studies, integrating the interconnect directly into their own proprietary control software, and building entire commercial product roadmaps explicitly around NVQLink's continued existence. That's the difference between genuine adoption and empty corporate signaling, and by the middle of 2026, the evidence pointed unmistakably toward the former. And the reach extended far beyond individual startups, too. Rigetti Computing, a company technically competing directly against Google and IBM for quantum hardware dominance, forged what industry analysts describe as a deep partnership with NVIDIA, aiming to integrate its own quantum hardware directly with NVIDIA's GPU-accelerated classical clusters, an approach widely considered the most realistic near-term path toward genuine quantum advantage. Germany and Japan both implemented NVIDIA's quantum software platform inside their own national quantum technology initiatives. A Polish supercomputing center partnered with a British quantum startup called Orca Computing, and with NVIDIA directly, specifically to accelerate hybrid quantum classical high-performance computing. An Israeli quantum startup called Classique teamed up with both NVIDIA and the German automaker BMW, applying quantum algorithms combined with GPU-accelerated simulation to optimize the physical architecture of electric vehicle components. Even JP Morgan Chase, a company with every incentive to move cautiously and only invest in infrastructure it genuinely believes will deliver real, near-term value, began testing quantum-adjacent security applications on its own network, and separately partnered with AMD and a company called Oxford Quantum Circuits to explore how quantum computing might address complex financial services workloads. Understanding exactly why so many fundamentally different companies, building fundamentally different kinds of quantum hardware, all converged on this same specific piece of infrastructure requires understanding the precise technical problem sitting underneath all of it. According to NVIDIA's own technical documentation, quantum error correction decoding represents a massive single-user inference task that has to run continuously alongside quantum processing itself, with essentially zero tolerance for delay. A quantum processor needs access to high-performance co-processing, capable of responding to function calls faster than its qubits naturally decohere, and fast enough to track subtle system drift, the gradual wandering of gate fidelities that happens as quantum hardware operates over time. This is a genuinely narrow, genuinely technical bottleneck, but it's also one every single quantum hardware company, regardless of whether they're building superconducting circuits, trapped ions, neutral atoms, or photonic systems, ultimately runs into in exactly the same form. That universality is precisely why companies as different from each other as Dirac's silicon processors and Quandela's photonic systems both found genuine independent reasons to build on top of the exact same interconnect. In April of 2026, roughly 6 months after NVQLink's original launch, NVIDIA added a genuinely new layer directly on top of this interconnect. And the specific numbers behind this addition deserve close attention because they answer the "why does this matter" question with real precision. The company released Ising, described as the world's first family of open-source artificial intelligence models, purpose-built specifically for quantum computing workloads, tackling two of the field's most stubborn bottlenecks, calibration and error correction decoding. Ising calibration, a 35 billion parameter vision language model trained on real quantum experiment data, compresses the traditionally manual days-long process of tuning a quantum processor's qubits down to mere hours. And according to NVIDIA's own published benchmarks, it outperformed Google's Gemini 3, OnePro, Anthropic's Claude Opus 4, 6, and OpenAI's GPT-5, 4 on a newly introduced benchmark specifically designed to test quantum calibration tasks. Think about the weight of that specific claim. NVIDIA isn't simply saying its specialized quantum tool beats other specialized quantum tools. It's saying a model purpose-built for this narrow technical task outperformed some of the most capable general-purpose artificial intelligence systems on the entire planet, at least on this one specific job. Ising decoding, the second half of this release, runs up to 2.5 times faster and 3 times more accurate than pi matching. The open source decoder most quantum research groups around the world currently rely on as their default tool, while requiring 10 times less training data to reach that same level of performance. Within days of launch, adoption spanned an extraordinarily diverse range of institutions: Fermilab, Harvard's Engineering School, the University of Chicago, Sandia National Laboratories, Cornell, and the UK's National Physical Laboratory among them, spanning superconducting, trapped ion, and neutral atom architectures simultaneously, the exact same cross-competitor pattern already established by NVQLink itself. Now, here's where this story earns the honest, grounding caveat every genuinely exciting technology breakthrough deserves before it fully earns your trust. Because celebrating this connection without confronting what it explicitly does not solve would be doing you a real disservice. Quartz's own detailed reporting on this exact story states the limitation directly, in a single sentence, worth repeating word for word. One thing quantum is not going to do is make the data center energy crisis go away. Read that again and sit with exactly what it means for the broader excitement surrounding this connection. The gigawatt-scale electricity demand currently driving AI data center construction across the entire world, the same demand forcing utility companies into desperate negotiations, the same demand pushing tech giants toward nuclear power contracts. None of that gets solved simply because quantum processors are learning to connect to classical GPUs at microsecond speeds. This connection isn't a rescue mission for the energy crisis already unfolding inside AI data centers. It's something else entirely, a new specialized capability being carefully layered on top of an existing infrastructure problem that this specific technology was never actually designed to fix. So if this connection isn't solving the energy crisis, what exactly is it doing? And why does the specific framing sitting inside this video's own title, "Here's Why It Matters," genuinely deserve a real, substantive answer rather than pure marketing enthusiasm? The honest answer requires understanding a shift industry insiders themselves have started describing openly. Petrina Steele, Equinix's global lead of emerging technologies, offered a genuinely useful reframing during industry commentary earlier this year. It is no longer a question of whether quantum technology will live up to its substantial hype, she explained, but how it can be integrated with existing systems. These kinds of infrastructures have to live together. Notice exactly what's being taken for granted in that specific sentence. Someone whose entire job depends on accurately predicting which infrastructure trends deserve genuine investment has already moved past the tired debate over whether quantum computing is real or overhyped. Her attention has shifted entirely toward the harder, more practical engineering question of how two fundamentally different kinds of computing infrastructure actually learn to live together inside the same physical space. And NVQLink is, very specifically, the answer to that exact question. As Gutenberg University Mainz and Mainz University of Applied Sciences built their system around detailed three-dimensional scans of the actual physical tablets, capturing the true depth and shape of each individual wedge rather than a single lighting-dependent snapshot of it. Their team trained the system using nearly 2,000 separate cuneiform tablets, including roughly 50 drawn directly from their own university's collection, using a specialized method called RCNN-based polygonal wedge detection, learned specifically from carefully annotated three-dimensional renderings paired with mapped photographs of publicly available cuneiform data. Think of this approach almost like giving a computer genuine depth perception for the very first time, rather than forcing it to squint at a flat image and guess at shapes that were never meant to be viewed flat in the first place. The results speak for themselves in a genuinely remarkable way. Tablets that once required a trained assyriologist, hours or even days of painstaking, careful reading, can now be processed by the system almost instantly. And because the output is genuinely searchable, digitized text rather than an image a human still has to manually read, scholars can now search and cross-reference the contents of multiple tablets simultaneously, opening up entirely new categories of research questions that simply weren't practical to ask before this technology existed. A separate, equally important breakthrough came from a team at Tel Aviv University, and it tackled a slightly different piece of this same underlying puzzle, the challenge of dealing with just how wildly inconsistent individual cuneiform signs can look, depending on which specific scribe carved them thousands of years ago in a specific region at a specific moment in time. Their system, called ProtoSnap, takes a genuinely elegant approach to this problem. Rather than trying to directly recognize a messy, irregular real-world sign, ProtoSnap uses a generative artificial intelligence model to align that irregular sign with a clean, standardized prototype reference character, effectively snapping the messy, real-world version into place against an idealized template. Think about why that specific technique matters so much. It's the difference between trying to identify someone's handwriting by comparing it directly against 1,000 other people's wildly different handwriting samples, versus first mentally translating that handwriting into a clean, standardized font, and then comparing that cleaned up version against your reference material. By dramatically improving character recognition this way, ProtoSnap has proven especially valuable for rare or highly variable signs, exactly the kind of signs that used to cause the most trouble for earlier, more rigid recognition systems. Now, here's where the story moves from simply reading individual signs into something considerably more ambitious, genuine translation, and understanding exactly how far this specific capability has come reveals just how quickly this entire field has been accelerating. Researcher Shai Gordon and colleagues at Ariel University developed an AI model capable of automatically translating Akkadian cuneiform text directly into fluent English, essentially functioning as a Google Translate style tool for a language that hasn't been spoken by anyone on Earth in roughly 2,000 years. Akkadian deserves a moment of its own context here, because it isn't some obscure minor footnote in ancient history. It's one of the earliest known Semitic languages, part of the same broader language family that eventually gave the world Arabic and Hebrew, spoken across ancient Mesopotamia, primarily within the Akkadian Empire, in territory that today spans parts of Iraq and northeastern Syria. Akkadian scribes used it for an enormous range of purposes: administrative records, legal contracts, epic literature, and detailed scientific texts. And its original decipherment in the 19th century represented one of the great scholarly achievements of that entire era, finally opening a genuine window into the ancient Near East for the first time in nearly 2 millennia. Read that again and sit with the genuine weight of what's happening here. A language that took 19th century scholars decades of painstaking comparative work to even partially crack is now being translated automatically by software in the time it takes you to read the single sentence. Somewhere in a climate-controlled archive, a clay tablet has been sitting in near total silence for roughly 4,000 years, its surface covered in tiny wedge-shaped impressions, pressed there by a scribe whose name we will probably never know. For most of human history, the tablet was effectively mute, its meaning locked away behind a script so complex it took modern scholars nearly 2 centuries to even partially crack it. This year, an artificial intelligence system read it in seconds. Read that again. 4,000 years of silence broken not by another uniquely difficult, in a way, most ancient scripts simply aren't. Cuneiform wasn't used for just one language. It was adapted and reused across roughly 15 separate languages from entirely different linguistic families, employing 3 completely distinct writing systems within the script itself: logographic signs representing whole words, syllabic signs representing sounds, and eventually even alphabetic signs. On top of all of that, cuneiform is fundamentally a 3-dimensional script, wedges pressed physically into clay rather than ink laid flat on a page, meaning the exact same sign can look dramatically different depending on the angle of light falling across it, or the precise angle a camera happens to be pointed from when someone photographs it. This is precisely why traditional optical character recognition, the same basic technology that lets your phone scan a printed document and turn it into searchable text, has historically struggled so badly with cuneiform. According to researcher Ernst Stutzner, working on exactly this problem at Martin Luther University Halle-Wittenberg, standard OCR systems are built to work with flat photographs or scans, something that poses essentially no problem for ink pressed onto paper or parchment. Cuneiform breaks that entire assumption. For cuneiform tablets, Stutzner explains, external factors like light conditions and viewing angles dramatically impact the accurate identification of certain characters. Think about what that actually means in practice. The exact same physical wedge, carved by the exact same ancient scribe, could be photographed by 2 different researchers under 2 slightly different lighting setups and produce 2 images that look meaningfully different to a computer trying to identify what sign it's actually looking at. This is not chaos. This is simply the genuine, stubborn physical reality of trying to digitize a 3-dimensional handwritten script using tools originally built for flat, 2-dimensional printed text. So how did researchers actually solve this problem? And what makes this year's breakthroughs genuinely different from earlier, more limited attempts? The answer starts with a fundamental shift in how these systems even look at a tablet in the first place. Rather than working purely from flat photographs, the team at Martin Luther University, working alongside researchers from